Hello everyone, I'll be covering acceleration in today's lesson. Just a heads up, there are a few questions for you to do at the end of the video today, so stay tuned for that. Okay, so we covered velocity last class, which is the rate of change of displacement of an object with respect to time. So it's basically the slope of a displacement time graph, right? It's the first derivative of the displacement function. And today we're doing acceleration, so that's the rate of change of velocity with respect to time, so it's dv dt, and since v is ds dt, then we can say that the acceleration is the second derivative of the displacement function. Okay, so that's how it's all connected. So the slope of the displacement is speed, and the slope of speed is acceleration. So looking at this first example, we see a VT graph here. Looking to figure out what we can say about the acceleration for this graph in various sections. So the slope of a VT graph gives us the acceleration. So basically all of these questions are asking for the slope, right? So the slope from A to B is positive and constant. So that means the acceleration is positive and constant. From B to C, it's flat, so we got zero slope, so that means there is zero acceleration. It's moving at a constant speed in this section. From C to D, it's increasing. You can see, like, if you were to draw tangents all the way through, they get kind of steeper, and then it's a bit constant in this section. From D to E, it looks as though it's decreasing, so it's sort of constant to start, and then it starts to sort of flatten out a little bit. So decreasing. And last, from E to F, it's getting, all the tangents are getting steeper and more negative. So from E to F, it's increasing in magnitude. Because it's getting, the tangents are getting steeper. All right, next example. The height of an object is given by this function where h is meters and t is seconds. Determine the acceleration of the object. So what we basically have to do is take the second derivative of this function. So we can determine the first derivative fairly easily. So 2 times negative 4.9, negative 9.8, and then t, so the exponent drops 1, and then derivative of that is just plus 20, and derivative of 5 with respect to t is 0. So that's the first derivative, or the speed, or velocity if you like. So second derivative, the derivative of this would just be negative 9.81. Sorry, just negative 9.8. I've got physics brain. So negative 9.8 meters per second squared. Negative 9.8 meters per second squared. Example number 3, displacement function of an object is given by this. Determine the velocity of the object when its acceleration is 0. So acceleration is the second derivative of the displacement function. So the first derivative is, so 4 times a quarter is 1, t cubed minus 9t squared plus 24t plus 7. There's the first derivative. Second derivative would be 3t squared minus 18t plus 24, and the derivative of 7 with respect to time is 0. So we want to find out when the acceleration is 0, so set the acceleration to 0. Looks like we can factor a 3 out of each of these terms. So we would be, whoa, that's a weird bracket, 3t squared minus 6t plus 8. So we need two things that will multiply to give positive 8 and add to give negative 6. So that would be that. So t squared minus 4 minus 2, that would give the middle term. Negative 2 times negative 4 is positive 8. So the time when the acceleration is 0 is at 2 seconds and 4 seconds. So now we just need to sub those times in for the velocity function. So I guess we could write velocity at 2 seconds. So take this, everywhere I see a t, I put a 2 in its place. So 2 cubed minus 9, 2 squared plus 24 times 2 plus 7. That would be 8 minus 36 plus 48 plus 7. So that would be 27 meters per second. And then the velocity at 4 seconds would be, so 4 cubed minus 9 times 4 squared plus 24 times 4 plus 7. So 4 cubed would be 64. That'd be 16 times negative 9, so be there. 24 times 4 is 96 plus 7. Okay, altogether that would give you 23 meters per second. So those are the speeds or velocities when the acceleration is 0. Okay, next determine when the acceleration is positive. So we can draw an interval here. It's 0 at 2 and 4 seconds. I can write the factors out here. So 3, t minus 2, t minus 4, and then the acceleration is the product of these. So 3 is going to be 3 throughout, it's positive 3. T minus 2, so to the left of 2, so supposing I picked like t equals 0 or t equals 1, something like that, that would be negative. To the right of 2, so for example 3 minus 2 would be positive. To the right of 4 would also be positive, so like 5 minus 2 is positive. Okay, and then this one, t minus 4, if it was like 1 minus 4, that would be negative. If I picked 3, for example, 3 minus 4 is still negative. And then to the right of 4, like 5 minus 4 is positive. So take the product of these, negative times negative is positive. That would be negative, that would be positive. So the acceleration will be positive, negative, positive. So between, assuming we're starting at t equals 0, it's positive between 0 and 2. It's negative from the interval from 2 to 4. And then it's positive again from 4. And if we assume that the object keeps moving forever, it'll be greater than 4. So those are the intervals when the acceleration is positive. Next question. Position of an object is given by this function where s is in meters and t is in seconds. Draw a graph of the position function between 0 and 4. So you can plug in, so at 0 you would do 2 times 0 cubed minus 12 times 0 squared plus 18 times 0. That would be there. At 1 you could do the same thing. That turns out to be 8. At 2 works out to be 4. At 3 works out to be 0. And at 4 turns out to be 8. So just kind of making a guess, right, roughly. Okay, so that's done. Determine the velocity function and sketch its graph on the same grid. So we need to take the derivative of that to get velocity. So v of t equals s prime t. So it would be 3 times 2, 6t squared, minus 12 times 2, 24t, plus 18. Okay, and you can sub in values like we did for the position function. You could do for 0, then you could do for 1, and so on. All right, so at 0, it looks to be 18. At 1, it's 0. At 2, it's about -6. At 3, we're at 0. And at 4, we're 18. So velocity time graph looks like that. So that's v. Maybe just label s. Okay, so sketched it, great. Use the velocity function to determine the local relative max and relative min points on the position function and adjust your graph. So this point here, I would expect a max there because the first derivative is 0, and I would expect, or you would expect either a max or a min there, which looks like we have. And then here at 3, it looks like we'd expect a max or a min, and we have a min, so looks like we're in good shape, and I just happened to draw it roughly the way it should be drawn. Okay, so no need for adjustments. On to D, determine the acceleration function and sketch its graph. So take the second derivative. You can see it will be 12t, right, 2 times 6 minus 24. So 12t minus 24 is a linear function. So the y-intercept is at -24. At 1, it's -12. At 2, it goes through 0. At 3, we're at 12. And then 4, we're up at 24. So our acceleration graph looks like that. Okay, that's sketched. All right, next determine when the acceleration is equal to 0. At this time, what occurs on the graph of the velocity function and the graph of the position function? Graphically, right, it's there. That's when the acceleration is 0. What does that mean for the velocity? So that means, because the acceleration, right, the acceleration is the slope of the velocity function. When the acceleration is 0, that means we should either expect a max or a min for the velocity, right? And we do have a min there, right? And the reason for that is because the slope, like the tangent of the velocity graph, is flat at that precise moment. So that means the acceleration will be 0. Okay, and what that means for the displacement function graphically is we'll have a point of inflection, as you can kind of see. So it's curved down and then it goes curve up at that point. So that's what it means when the second derivative is 0. So the velocity function will have a max or min when acceleration is 0, and the position function will have a point of inflection when acceleration is 0. So that's graphical, right? So, but what's happening in reality? So what roughly is the object doing in reality? Thinking back to our physics 20 days, the position function, it's going kind of back and forth, right? It looks almost sinusoidal, a bit like an object like a pendulum or something undergoing simple harmonic motion. So at this particular point, when the acceleration is 0, the speed is at a max, it's at negative, and the position function is at a point of inflection. So if we think of this maybe as like a pendulum, right? So remember back to that unit. We have a max acceleration here, and velocity is 0. And then here we have acceleration equals 0, and velocity is at a max. So it's basically what's happening at this precise moment is it's sped up to its to its highest speed, and the acceleration is momentarily 0. Okay, so I guess that's it for today. Your questions, if you could take a picture of your work, do question number 1 from the textbook today. So that would be page 128. So do question number 1 if you could, please. A through E. And do as well question number 3, C and D, as well as question number 9. Okay, I guess that's it. Take care.